Okay. Hello. Excuse me. This is the last test that that I'm doing for now. This is going to be fall 2017. It's a pretty short and sweet one, and so let's get going. We're starting off with the normal Lagrange multiplier question that is very similar to all the other Lagrange multiplier questions, and we know for this we need, the drill by now. We need an fx, an fy, an fz, and we set these guys equal to gx lambda, gy lambda, and gz lambda, where g is our constraint and f is our function that we're trying to maximize or find the extrema of. So solving, we're going to get 2 equals 2x lambda, we're going to get 1 equals lambda, and we're going to get 4 equals 2z lambda. And this is a very weird case where we actually know what lambda is, so we can skip a lot of steps and just solve. So if lambda is equal to 1, x has to be equal to 1, and if lambda is equal to 1, z has to be equal to 2. And then we can plug both of these guys into our constraint, like we always do, to find what y is equal to. So 1 squared plus y plus 2 squared equals 6, so y equals 1. Add that guy in there. And since this is a maximum, and it says we're assuming it has an absolute maximum and no minimum, so we know that this is going to be our maximum value, we can plug that guy into our f function up here, and we'll have our answer. So 2 times 1 plus 4 times 2, this is just going to give us 11. And this is pretty much the most painless Lagrange multiplier question we've been given, which is pretty nice. Okay, I'm going to make a little room here so it's not in the way. We've got a double integral, changing the order of integration. First off, every time we need to make our inequalities. So root x is less than or equal to y is less than or equal to 2, and 0 is less than or equal to x is less than or equal to 2. And if we graph this guy, we're going to get root x and 2 as our bounds for y, and then x is between 0 and 2. So there's a little area. We've got to rearrange this guy. Integral dx dy. The integrand stays the same, so y cosine of y to the 4th is still there. But drawing a line parallel to the x-axis, we see that we hit x equals 0 first, and then we hit this parabola x equals y squared second. So y squared. And then our bounds for x our bounds for y, our outer integral, the bounds change. Y's extrema run from 0 to 2, so we'll put 0, 2 in there. So now solving, we have no x in here, so all we have to do is multiply by y squared. So y cubed cosine y to the 4th, 0 to 2 dy. We can just what's it called? U sub it. So we'll do some u sub and take the integral, and we will get sine y to the 4th over 4, evaluated on 0 to 2, which is sine 16 over 4, and we know that sine 0, 0. So sine 16 over 4 is our answer. Okay, we got a polar integration question. The region between the circles. Let's see. We'll make a nice little graph. We got the circle's radius 1, and the circle. This isn't radius 2. This is radius root 2. Important to recognize. Radius root 2. Okay, and we're looking for this integral right here, except theta we know is we're not dependent on theta at all. We got to get all this area in here, and in order to get that we have to go around 2 pi. So this is really a single integral where we're just multiplying by 2 pi on the outside, and r is running from 1 to root 2. And instead of doing it graphically, you can always recognize that x squared plus y squared is r squared. And so 1 equals r squared, r equals 1, and 2 equals r squared, so r equals root 2. Okay, so evaluating this with e to the r squared, remember we gotta always multiply by r, dr, we'll get e to the r squared over 2, evaluated on 1 to root 2, is e squared over 2, and then e over 2. And then if we multiply everything by 2 pi, we're going to get pi e squared minus pi e. And pi e squared minus pi e is right there. Okay, we're finding the part of the unit ball, radius 1, center at the origin, that lies between the cones, phi equals pi over 6 and phi equals pi over 3. So let's give this guy a little graph, because that's, I mean, you could just set up your integrals, but it's good practice to always draw these things out. So we've got phi equals pi over 6. That's my vague representation of pi over 6. And then phi equals pi over 3, which is right here. And we're looking for this area. It's kind of a weird cone with a cutout in it. And we know that this is the unit ball, which is a kind of silly term, but whatever. So we know that rho is equal to 1. So we can set up our double integral, because we know we can just multiply by 2 pi, because we're not dependent on theta. We got to go all the way around eventually. We know that phi runs between pi over 6 and pi over 3, and I'll just be clear and add our d rho d phi out there. And we know that our rho runs between 0 and 1, and we got to add our basic ingredients to the integral, which is rho squared sine phi. Okay, and this is a pretty easy one to solve. We're going to get rho cubed over 3 evaluated on 0 to 1, so 1/3. And we'll add that back in. So sine of phi over 3, a value. Nope, we're not evaluating yet. We gotta integrate from pi over 6 to pi over 3 d phi. That's a theta. It's supposed to be a phi. Will be negative cosine of phi over 3 on pi over 6 to pi over 3. Oh, getting windy. And this thing right here, cosine of pi over 3 is 1/2 times negative 1/6 is negative 1/12. And pi over 6, cosine of pi over 6 is going to be root 3 over 2. So this is going to be negative root 3 over 6. We're multiplying by 2 pi, so we can set this up as 2 pi root 3 over 6 minus 1 over 12. I did something. This is not 1/12. This is 1/6. I did my basic algebra wrong in there. Sorry about that. And we can just factor out a 6 to get pi over 3 root 3 minus 1, which is what they have right here. Okay, this is a little bit of an odd question. They don't ask this very often. They're asking for the incorrect setup for one of these integrals, and it can be really daunting looking at all this crap, trying to figure out what in the world they're looking for. But there's actually a very clean and easy way of solving this. We know that, say, we're taking an integral with respect to z. It has to be the bounds have to be in the form z equals, right? And so in this case, we know that whenever we're taking a dx, it has to be a square root, because otherwise it'll just be x squared. Oh no, I hope that wind's not too loud. Because otherwise it would be x squared equals z plus. I'm losing my train of thought, but essentially if you can see this, it'll be very helpful how we need square root whenever we're taking the derivative with respect to. God, people are loud. With respect to. I'm just going to restart this question. Okay, I'm restarting this question due to loud people and the wind. So, taking a look at this kind of unusual question, we hardly ever get this kind of thing. It's asking for the incorrect setup for this integral in rectangular coordinates, and it can be pretty daunting just taking a look at all of all these options. Like, how in the world am I going to find that tiny little thing that's off? It's actually relatively easy. So we know that whenever we're let's say we're taking an integral with respect to y, that needs to be in the form, the bounds need to be in the form y equals something. But in this case, one thing that we can look for is that any integral with respect to x has to have a square root in it if it also has variables in it. And so that's one thing we can look for down here. We see that this dx has a square root, so we're happy with that. This dx has a square root, we're happy with that. But this dx, no square root. And we actually don't even have to check that these guys are right. They have to be right because this one has to be wrong, and there's only one incorrect setup. And so that's a pretty goddamn. I know that the wind gets pretty loud in these headphones, so sorry about that. So that's a pretty quick and easy way of figuring that guy out. Okay, so for this next one, we're not evaluating. We're just rewriting this integral in cylindrical coordinates. And so let's see. We're gonna have a triple integral dz, dr, d theta, and we can just give this guy a graph. So on the xy plane, we're going to be running this thing right here. Root 4 minus y squared is just the hemisphere with radius 2, so from -2 to 2, and we can turn all of these guys into things in terms of r. So this is going to be 8 minus r squared. This is going to be r. And this is going to be r. But we got to remember that we're also multiplying by r. So this guy and this guy are automatically out, and it's never none of the above. So we're already down to two answer choices. And the only difference is the theta bounds that they have in here. And if we look, y is running from 0 to 2. Well, the only way for y to run from 0 to 2 is if we go from theta equals 0 to theta equals pi over 2. So there's our answer there. Okay, surface area integrals. Again, these are not on the exam, but they're still good to do, just to know. Pretty useful. So we know that for a surface area integral, the integrand is the square root of fx squared plus fy squared plus 1. And we can find that pretty easily. Fx, where f is this guy, is going to be negative 2x. Fy is going to be negative 2y. And that's all we need. So we can set up our integral. We know that we're going to have a square root 4x squared plus 4y squared plus 1. And we're lying above the xy plane. And so remember that we're dealing with the projection of this guy onto the xy axis. So it's where z is equal to 0. So if we set z equal to 0 and sub in r, we're going to have 0 equals 2 minus r squared. So r is going to run from 0 to root 2. Hope that's easy for you to see. And since we're subbing in r there, we might as well sub in r here. We're going to get 4r squared, and I'll bring this in a little bit, plus 1. We got to add our r, because now we're in polar coordinates, dr d theta. And in fact, wait a sec. Nope, we're good. So our r is going to run from 0 to root 2, and our theta is going to run from 0 to 2 pi. But really, we're not dependent on pi. God, it's windy. So we can just put 2 pi outside here. So evaluating this integral will save a little time. This ends up being 1/12 for r squared plus 1 to the 3 halves, evaluated on 0 to root 2. If we plug in root 2, we're going to get 9 to the 3 halves, which is 27. So 27 over 12. And this guy, when we plug 0 in, is going to be 1/12. So 26 over 12 times 2 pi. Well, this is just the same as 13 pi over 3. And we're done. Okay, a vector field. These are kind of daunting too, because it's often not clear what to look for, but this one's actually kind of easy. We see that x the x component of our vector in every case is constant. So any graph where the x component of the vector changes, so I'm talking like, you know, going from that to that, anywhere is wrong. So, this one, automatically wrong. That's a bigger component than that. So that's out of the table. This one's off the table. This one's definitely off the table. And so is this one, where it's kind of funny. This one's the only one where, well, in this case, only x is changing, and that's the one thing that we don't want. And if we look here, b actually fits both of these cases. The x component is always the same. I hope you guys can kind of tell. It's kind of hard to look in there. In fact, we can zoom in. And the y is dependent on x. So as we go farther negative in x, y gets more negative. As we go more positive in x, y gets more positive. And so both those relations hold. Okay, we got a line integral, and we got to make a line segment. So we're starting at 1, 1, 1. We're going to 3, 2, 3. And so we know that we can just set this up as x equals 1 plus 2t. Y equals 1 plus t, and z equals 1 plus 2t for 0 less than or equal to t less than or equal to 1. That looks more like a j, but it's okay. So now that we have that, we know that for ds, we need to not only substitute these guys in for our x's and y's and z's, but we need to multiply by the square root of the sum of the squares of the derivatives of all these components, which sounds a lot fancier than it is. So the dx is just 2, dy is just 1, dz is just 2. So we can square all these guys. We're going to get 4 plus 1, which is just root 9, which is just 3. So we know that in order to turn this into dt, we're just multiplying by 3. Taking our overall integral, we know that our bounds are between t runs from 0 to 1, and now we can just substitute all of our values in and multiply by 3. So x is going to be 1 plus 2t, 2y is going to be 2 plus 2t, and z is going to be 1 plus 2t, and then all this is getting multiplied by 3. Now cleaning this up a little bit, we're going to get 1, 2, 3, 4 times 3 is 12, plus 1, 2, 3, 4, 5, 6 times 3 is 18t dt. So integrating, we're going to get 12t plus 9t squared evaluated on 0 to 1, and this is 21. And we're done. Okay. Oh wow, this is the last question I have to do today before I get to figure out how to upload all this stuff. So sweet. It's only been like 4 hours. Okay, we're evaluating an f.dr. This is a type of line integral that theoretically we do not have to do on our exam. There are no vector line integrals, but it's still good to know, and it's still pretty quick and easy. So they give us our bounds for t, and they give us r. We know we're going to need r prime, so let's grab our prime of t. R prime of t is going to be 1, 2t. Great. Okay. We also need to sub in our I and j values for our x and y values over here. So xy is going to be t times t squared, and we know that we need to dot that with the x component of the derivative of our path vector. So that's just going to be dotted with 1. And then we're going to add, well, in this case, subtract y, which is t squared, dotted with the derivative of our y component, or well, really the j component of our of this guy, so 2t. And so simplifying all that out, we're going to get t cubed minus 2t cubed, integral from 0 to 1 dt. And this is just negative t cubed dt. Sorry about that, people are loud. And then this integral is the integral from, we're evaluating. So negative t to the 4 over 4 on 0 to 1 is negative 1/4, and we are done. Okay, Goddamn, that took a long time. But I hope this is helpful for you guys. I'm going to try to link all of these questions to individual boxes in the spreadsheet, so you can like click a box and get the answer to the question. So that'll be pretty cool. And yeah, I hope you guys had as much fun listening to all my mistakes as I did in making them. Thank you for listening.